Are you ready? Now we have had the cabinet of plane figures, and you remember we gave the full classification. Now today I'm going to look at the solids with you, and again we must give the full classification. And when we have the solids with the children, they don't have to be solid all the way through. It's the surface that must be unbroken. See? And we must have them of a reasonably small size, not too, there are some enormous ones on the market, but much too big and heavy. You see, they want to be the size that a little child could comfortably hold in the hand and feel them and look at them. You see, this is an ideal size. Or these, which I have borrowed. These wooden ones are they're very nice. I like them better than the plastic. They're very beautiful, very much nicer to feel. But I have some in wood at home that were made before in the 1930s, but now they are so expensive to have made in wood that it's really not practical unless you can make your own. Now, when we use them, when we classify them, we first we have these 4 groups, and as I go through, you will see how the groups must be kept together. And we would begin with the regular ones. And I'll put the names up for you, because you may not be familiar with all the names. Possibly you didn't have them in your mathematical education. I didn't. But now there's a big return to the study of the polyhedra, and the children are studying them in math. Well, these first 5, first of all, now polyhedron is a singular. That just means many. Poly means many, hedron means face, many face. And the plural is polyhedron. We use these words with the children because children pick up words very easy, and as they're always saying to you, it's no more difficult for them to learn the word polyhedron or polyhedra than it is to learn staircase and automobile and elevator. You see, the difficulty is only in our minds. And if we give the proper words at this stage, they just pick up the vocabulary, and they pick it up at an age when they learn words easily. And it means that later on, when they come to the study of these things in the regular schools, that they already know the terminology. And that means that the subject is going to interest them more. And they don't suddenly have to learn all these difficult words at an age when they don't take to words so happily. Well, now there are 9 regular polyhedra. There are only 9 regular ones, and Plato describes 5. And so the 5 that Plato describes are called after him. Now this one, the fewest number of the terms you use, this is a face. You speak of a rock face, don't you? That's a face. This is the edge. This is the apex. Apex, the plural is apeces. sometimes spelt with an I, sometimes with an E. But that's the singular and that's the plural. Apex is quite a common word, so edge, face, they're not strange. We use those terms when speaking with the children. Now this one has the fewest possible number of faces that will enclose a space, and that it has 4 faces, and each face is an equilateral triangle. 4 faces, and so it's called a tetra. Tetra means 4, tetrahedron. This one, 6 faces. Each face is a square. Now, the ordinary everyday word, of course, is cube, but it's a hexahedron. If you're using the Greek terms, you want to use the Greek terms throughout. Six faces, each face is square. The next one, rather pretty one, has 8 faces, and each face is an equilateral triangle. 8 faces, each face an equilateral triangle. When there's a triangular face, if it's a regular polygon, then a regular one, it must be equilateral triangles, mustn't it? Otherwise it wouldn't be regular. So any polyhedra that has triangular faces is bound to be equilateral triangles. Now, the next one has 12 faces. And as you can see, each face is a pentagon. So that is a dodecahedron. Dode meaning 12. This one, really the prettiest of them all, has 20 faces. Each face is an equilateral triangle. Icos is 20, so it's an icosahedron. That all right? Now I don't have the other 4 regular ones to show you, but I have a picture of them, and you would need to construct them for the children. There. I don't know if you can see. Can you see this postcard? Well, on this side are the 5 regular ones, plutonium ones that I've just shown you, only they're made with each face in a different color. And later on, when the children were older, we would like to give them these, with each face a different color, because that makes it easier for them to count the faces, count the 8 inches, count the edges, and arrive at a common denominator, as it were. The other 4 regular ones are star-shaped. They are very beautiful. And you can see them, can you? Now, strangely enough, these were not known. The ancient Greeks didn't find how to make these. 3 of them, I think it was the first 3, were made by the mathematician Kepler. Very bad at dates, wasn't he? Does anyone know his dates? Somewhere around 1500, was he? He was a very... And he made 3, and a man called Poinsot made the 4th. Poinsot made his around about 1820, somewhere around there. So they are the Kepler-Poinsot polyhedra. It's not difficult to construct them, and they are made by additions to the 5 plutonium ones. In fact, it's not difficult to understand how they're made. This one, which is the small stellated dodecahedron, is made by prolonging all the edges of the pentagons of each pentagon. You do know how to make a perfect star, don't you? It's very useful if you don't know how to, especially at Christmas time. You draw a pentagon. Drawing freehand, my pentagon won't be very a regular one. And you prolong each edge with a ruler. If my pentagon was a perfect one, you get a perfect star. It's a very useful bit of construction. The children can make perfect stars at Christmas time. Also, if you join the diagonals, you get another perfect star and another pentagon. Well, it is this triangle that makes 5 of them make a point. See, like this. That is used for making the small stellated dodecahedron. It's this triangle for making another of the stellar polyhedra, and it's this triangle that is used for making a 3rd. So you can construct them quite easily. Actually, you must have seen that diagram many times, because it was a diagram that the mathematicians took as a sign of their guild or brotherhood all through the Middle Ages. And then, because the mathematicians were thought to be such clever people, when witchcraft was rife, the witches, people practicing witchcraft, drew that on the floor and did all sorts of hocus pocus, you know. Because their ignorance thought that that was a magical sign, just because the mathematicians were so clever. So it fell into disrepute. But those are the regular ones. Now, there are more semi-regular ones than you could have in the classroom. Archimedes made 13, or describes 13. The Greeks, of course, by the time they had learned the art of writing from the Phoenicians, so they could leave us these mathematical treatises. It doesn't mean that they discovered everything themselves. Some of these were used in ancient Egypt. This one, the icosahedron, has been found in an Etruscan grave, being used as a dice. So it doesn't mean that the shapes were not known. And nowadays, we use them a great deal. You see this one as a lampshade, don't you? 2 years ago, this one was made just about this size in bright reds and greens and iridescent colors as a Christmas tree ornament. You see, because now we have these days of plastic, it's easy to produce them. The dodecahedron was always used as a ball. If you sew 12 pentagons together and stuff it, you have a ball. Which of the games? Soccer has a ball made of 12 leather patches, you see. And so these are also used in architectural forms, see? And some of the gemstones solidify. Salt and sugar, I think, solidifies a hexahedron. I think topaz solidifies, I'm not sure, I may be wrong, solidifies as an octahedron. But of course, when the gemstones solidify, they're generally compressed, so you don't often get the perfect shape, but you can grow crystals in a jar and get really very good polyhedron. So they do occur in nature. Now Archimedes describes 13. I have a picture of them. And it's not difficult to see how he arrived at some of them. I think all the later ones are made by adding and subtracting to the original ones, the original 5. And you can see that if you took the hexahedron and cut off each apex in a regular way so that all these sides were equal, you would have one of these. This one. Because here you would have a triangle, and here you would have an octagon. See, so you would have one composed of triangles and octagons. And if you took a tetrahedron and cut off the apeces, what would you get? Triangles here, and what would you get here? Hexagons, yes. There it is. So this one is called the snub cube, and that's a snub tetrahedron. So when you look at these, you will be able to see fairly easily how they arrived at the geometry of these. And they're very easily made with constructional paper. So that I like to have the picture for the children in the classroom so that they do see how many there are. The mathematicians lately, some are spending their full time in studying the polyhedra, and I think in all now they have found something like 84. These are 5 of the most recent. They're very beautiful, but unless you see the geometrical drawing as to how they arrived at, they do look impossibly complicated, don't they? But very beautiful. I think the man who has really written most about them is Coexter, if you're interested. course, we are using them nowadays in architecture and so on, just because they are so beautiful. And this one, the stellated dodecahedron, I've seen used again as an electric light fixture. And in Dallas, Seven Flags is rather like this at Disneyland. They have strings of these all through the trees. See, it's easy to make them with plastic, clear plastic, and have a light inside. Probably you know somebody with one hanging up in their house. Well, we have these 5 regular ones, plutonium ones. We keep them in one container, and the children have them to handle and look at. And they must be the size that fits their hands. See, 2.5, 3-year-olds, 3.5s, before they can count, they like to handle them. And you can teach the names. I'm using trays, but you'll probably have a better container in the classroom. I haven't got all these things with me. Now we have 4 regular curved solids. The sphere, every point on the surface is equidistant from the center. We have the ellipsoid. The ovoid, now this is an oblate spheroid. If you took a rubber ball and pinched it, you would get a shape with flattened ends. This one is rather an extreme one, but it's important to have it because the world is that shape, isn't it? It's a sphere which is flattened at the poles. So it's really an oblate spheroid. There's one more that I've never seen made, but which we ought to get made, and that's a torus. That's like in a tube with a, it's this continuous ring. It's rather like a donut with a hole in it, in a tube. But you know it. Or just think of a solid tile. That's the only one I haven't got. Now, in my plastic set, I have everything except the ellipsoid. I must try and get the firm to make one. They copied them, they came to see ours, copied them, but never made the ellipsoid. And that it is important to have that. These wooden ones, 4 wooden ones I borrowed. In America you can get a bucket of these, and they don't contain, I think they only have the hexahedron. They don't contain the other regular ones. And they have the cone cut through all its elements, which you don't require until the children are much older. So you get many which are not useful, but you do get these 4 regular ones, and they are so nice, made in wood. I wish we could buy them separately. Now, another thing, the children then can have this set, which are kept again in a separate container, because they're a different group, and they can feel them and look at them and learn the names. And then another thing they like to do with these is to roll them along the floor. See? And in rolling them, they see the orbit. See? They will take this one will go in a great circular path. If you have a nicely pointed ovoid, it will spin round on itself. So each will take a different path. And of course they love doing that. Again, you can tell them anything interesting. It's obvious that this is an egg shape. You can show them pictures of the different birds' eggs. Very different shapes according to where the bird lays its eggs. If it lays its eggs in a nest, well, they can't fall out of the nest, so they can be very blunt, pointed eggs. But the seagulls nest in vast colonies on very high cliffs, and they lay their eggs on very narrow shelves of rock. And in most cases they can't make any nests because, it would just blow away in a high wind. So they lay 1 or 2 eggs on this bare shelf. They have to lay a very pointed egg, so that in a high wind the egg will spin in a circle instead of rolling off the edge. Yes, the children love to have all these details, and it makes them more interested in whatever you're studying in nature. So that group is kept together, and they handle them, they learn the names, and they can roll them in the orbit. Now you have the picture of the semi-regular Archimedean ones, and possibly pictures of some of the modern ones. Certainly the Archimedean ones. And you might like to construct them to hang up in the classroom. It would certainly be nice to construct 1 or 2 of the star-shaped ones, because they're so lovely. And as I say, they're not very difficult to do. But you must, here is a group of some of the semi-regular ones. You all know this one. Prism. N just stands for any number. So in this one I'm showing you, you see the end faces are equilateral triangles. You must be a regular hexagon. And the end faces are equilateral triangles, and the side faces are rectangles. This one, I've got 3 different examples. This one, you see the end faces are hexagons, but the side faces are rectangles. This one, the end faces are octagons, regular octagons, the side faces rectangles. If you wanted to differentiate between these 3, you would just say a triangular prism, a hexagonal prism, an octagonal prism. Again, we use these shapes. Many of our pencils, before they were pointed, were hexagonal prisms. So they're all around us. And then these are pyramids. I've got 2 pyramids here. This one has a square base, and as you can see, the side faces are isosceles triangles. This one has an octagon for a base, a hexagon for a base, and the side faces are isosceles triangles. So you could call this one a square pyramid, and you could call this one a hexagonal pyramid. Now, of course, I'm showing you right pyramids and right prisms. So there, that set, and if you had any other semi-regular ones, you could have them in that with that group. There, again, they're there for the children to handle and learn the names. Now, another semi-regular group. So we have our 2 regular groups, and we have our 2 semi-regular groups. And in this semi-regular groups, the solids have both curved and plane faces. You all know what this one is. Cylinder. The 2 plane circles with the ends and the curved side faces. And you know this one very well. Cone, yes. Plane face and the curved face. And this one. Hemisphere, yes. Hemisphere. So your cylinder, your cone, and your hemisphere. they will be kept apart from the others, because they're the other group with plane and curved surfaces. P-L-A-N-E, plane and curved surfaces. Now, up to 5 years of age, they're there for the children to handle and to learn the names, so they become really familiar with them. And the curve set they can roll. There's quite a lot they can do. After 5 years of age, you can give them the nets and they can construct them out of a construction paper. They can construct, as they get older, they can construct the plutonium ones with each face a different color. Different ways of constructing them. If you gave them the net for the tetrahedron, imagine that's the equilateral triangle. They just cut it out about 1/4 inch larger, and then they divide it into the 4. They join the midpoints and they get 4 equal triangles, you see. And now they just nick off each apex, slanting cut. They're going to make some little flaps, you see, that will stick down. They take a nick out here. There. See? Now, if instead of drawing the lines, you scratch the lines with a pin, the whole thing folds up more easily. If you just scratch the surface of your paper, it folds much more easily. And then you put a very fast-drying glue on the flaps. I usually put a piece of cotton on here so they can hang it up. And you turn the flaps in, the whole thing folds up and sticks together, and you have a tetrahedron. You do want to use a quick drying glue. That way you can give them the net for each of the 5 plutonian solids. They can also construct them. You can buy a kit, but in England we mainly we just have the thin milking straw, drinking straws, and it's a very good exercise for the children to cut them into inch lengths, 2-inch lengths, 3-inch lengths. We have a box of these, and then we use pipe cleaners. You have pipe cleaners out here? Well, I think you cut them each into about 3 pieces or about 4 pieces. I can't remember quite how long a pipe cleaner is. And you bend those at an angle, and you can put the 2 sides down 2 straws, and you can join the straws together. And at first they like to construct all the plane figures. In doing it, they learn quite a lot. I had a little girl last year. She was barely 6, and she was taking different size straws and trying to make all the different triangles, hinging them together. And then she came to me and she told me, I've forgotten how she said it, but she did tell me that she always had to have 2 sides, greater than the 3rd. She realized there was this proportion before you could construct a triangle. There had to be a certain, if you had took one side that was too small, you couldn't get a triangle out of the 3 pieces. And then, when they're used to constructing the plane figures, they can construct the solids. But of course it will only be an outline, so an an outline of solid. They make up all sorts of ones, regular and irregular. But I think it's important to construct them out of paper first, because then you're making the solid ones. So that's much of the handwork we do with children is handwork that is also teaching them something. We're not just always messing about. But it's a lot of it is just sort of time filling. They can construct the cone and the cylinder. It's not so difficult. But that they do like doing, and making them, because they are learning a lot about it. So those are two rather nice ways of doing it. All right now, do you want to ask anything? I have very kindly got a second set with the names on for you. But it's a lot to if you're not used to it. Again, as soon as the children are beginning to read, you can put the written names on each tray, and they like to put out the solids and to read the written names. And if you notice, they're not so difficult. See? And they're almost phonetic. So they're very early in their reading, on the reading scheme, they can read most of the names and put them against the solids.
I have two questions. Did you have a name for the classification that included the sphere, the ellipsoid, the ovoid?
Those are the regular curved figures.
Oh, regular curved. So then, and then that's the difference between the regular curved and then the semi-regular.
I don't have any semi-regular curved. These are semi-regular, but they are curved and plain faces.
Why are they called semi-regular?
Because in a regular one, you see, the dodecahedron is composed of 12 dodecans, all of the same size. Therefore, all your apeaches will be the same. All the angles of the apeaches will be the same. I could have, this is a right pyramid, but if I had one where these angles were different, I would have a pyramid going this way, which would not be a right pyramid.
Where are you getting your right angle?
I never said I had to have a right angle.
Why would we call it right angle?
Well, this is the term. It means a regular one.
Oh.
It's a term that is used.
Oh, all right.
That these are semi-regular, because this one is composed, you see, of two hexagons and rectangles. Therefore, the angles at your apex will be different. See, in fact, here you get two right angles and an obtuse angle.
So are the regular shapes made of one shape?
Yes, they have to be.
And then, but now on the
regular ones.
postcards that you showed us, some of them were composed of two different shapes.
No.
The more complicated ones by
No.
coexistent study.
No. These are the 9 regular ones I showed
Oh, okay.
you.
The other ones are called semi-regular.
Yes, these are semi-regular. They're great. As I say, we have, I think, around 84 altogether nowadays, of which 9 are regular.
So the regular pyramid is not actually a regular shape?
It's not a regular pyramid, it's a right pyramid.
Oh, I see.
They are semi-regular figures. See, it's composed of more than one.
Do you do the exercises with the children that I've seen it somewhere, blindfolding the child and having some of the shapes in the bag?
We don't.
You don't do that?
No, neither did Dr. Montessori, because it's really important to look at them. You see, it's not knowing them by touch, it's knowing them by sight that is so important. I mean, certainly children do feel them. There really isn't any value in knowing them by touch. You want to look at them and see that these are bending. And later on, if you construct them with each side in a different color, then it's easy for them to count the number of sides, the number of edges and the number of appendages.
I think the assumption was that you'd really know the shape then if you could distinguish.
I think, well, we want them to know them by sight. We do not do this blindly.
So, in introducing a child to these shapes, do you just bring them over to the table?
Yes.
Do you do any lessons?
Well, first of all, he has them to feel and to look at. You know, just to handle. When I say handle, just to hold them in his hands and look at them. In fact, when you handle this one, you do sort of begin to realize how sharp the angles are. Whereas here, no, they're obtuse angles, and it's quite a different feel. But we want him to look at them just as much as handle them. Sight is really the most important element here.
So you sit with them while
You don't have to sit there, no. And then when they have handled, and they're always doing so, some children are very fond of them. I had two students who lived in my house, and they had a little girl of 15 months, and I had a box of these on my table. And she just loved them. She only had these sort of 2 words. She wasn't that at all hard. And she used to always like to come in the early morning when I was opening the post. She used to come rushing in, saying, "Hedrons, hedrons." And it was ridiculous. One of her first words was hexahedron. She adored them.
Did you give an introductory age then? Did you say anytime 2.5 to start?
Yes, when you have them in the nursery. It's very good to have these mathematical things about in the nursery. It's the age of the absorbent mind. And this is one of the pieces we give them. But of course they have to handle them, recognize them, and then later you teach the names. And you can say, are you going to look at the polyhedra this morning? You use any terms as though they were everyday words.
Would you discourage them from trying to build things for them?
Yes, and not you. If you mean are they used as blocks? No.
So I mean, if they start to make how to make towers and stuff.
No. But if a child is fitting these two together, see, he is finding there is a relationship in the surface of the same size. Or if he's fitting these two together, you see, there's a relationship. You wouldn't stop that. But if he's going into fantasy with them, yes.
The two trays have polyhedra. And is there a name for the curved solids, or you simply call them curved solids?
I call them curved solids. I'm not sure if they also rank as polyhedra or not.
And the same
Probably
with
do.
the sphere and the ellipsoid?
Oh, they're curved. No, these polyhedra means many faces, and they really actually only have one curved face.
So you simply call those the curved solids?
Oh, yes. I've never learned any other name for them. Any mathematician here who knows better? But they are so nice in wood. I'm sorry we can't get all of them in wood now. It's so much nicer to feel and to have. But in plastic, they are so inexpensive. And just when I got a quote on making this icosahedron, just this one alone cost about $25 to buy. So it makes it unrealistic. But any of you who can do carpentry could make it very well. I have a set which I bought in England, which the husband of one of my students made for me. It's a beautiful set. I also have the old set in which each face is a different color. All right then.
Would you call this a preparation or anything like for math or?
Oh, it is. You didn't call it a preparation. It is mathematics. All right then. Try to have your break Now, naturally, your children do see these shapes in the environment, see? And they will often say that this is a ball, for example. And, I mean, if they do, that's fine. See, it's intelligent, but you can say to them, yes, a ball is a sphere. See? And if they say to you that this is a box, well, not all boxes are hexahedrons. See, they may know, but I don't know if they would know the word cube here for anything, would they? Cube, would you say a cube of sugar? Ice cubes. Oh yes, you have ice cubes, you see. And then, well, I don't think they're really cubes, are they? No. You see, so they're cuboids. You see, and you can point this out to them. But you will have things that are hexahedrons, and you can tell them that hex means 6, and anything with 6 equal sides would be a hexahedron. But you mustn't say to them, this is a ball. You see, let them notice it, encourage observation, but don't begin by teaching those words. And it's obvious that that's the shape of an egg. See, well, you can tell them, yes, ovoid means egg shape. So that's all right, and they will see there are certain containers which are cylinders. Most of our tinned food comes in a cylinder, doesn't it? So when they make this intelligent observation, that's fine. But don't be like Sesame Street, which held up a balloon and called it a circle. It's a sphere, a round balloon. But you don't have to encourage that. It's only when they observe for themselves. Just as when they learnt the plane shapes, you know, then they would come up and say to you, my button's a circle or my plate's a circle. You see, which is, they immediately begin to apply their knowledge, which is so good.